Hey guys, hello everyone and welcome to the channel. So today in this particular video we are going to revise chemical kinetics. Now before starting this video I would like to tell you that this is not complete chemical kinetics. Okay, I'm not going to include each and everything in this video because that's not possible, right? But all the major things which are there from the topic, all the major points, all the major formula, all the major graphs are going to be included in the video. All right, so I would highly recommend that if you have separate notes of your own, or if you have like a short note or micro notes regarding this topic, so revise from that as well. This video will just help you to do this topic or to cover this topic in a very short interval of time. All right, and one more important thing, that while watching this video, if you feel that some point is missing in your notes and that is mentioned in this video, so you can just mention that down. Okay, you can just write that down. Now before going into the video, let me inform you regarding the Unacademy classes of mine which are running on the platform right now. I'm going to start two new courses. One is going to be for GATE 2021 and the other one will be for the next CSIR net batch. Okay, so a fresh new batch is going to start on Unacademy platform. Those are going to start from the first week of December. So all the details and the other things regarding the class I'll tell you guys in a separate video. But if you have any query regarding how to join the class and other things, you can ask those queries in the email provided in the description of this video. All right, now having said that, let's continue with our video. Alright guys, we'll start from the very basic, that is rate law equation. You know that if a particular reaction is given like this, that small a moles of A is reacting with a small b moles of B to give you small c moles of C and small d moles of D, then the rate, according to the rate law equation, the rate of the reaction will be given as k a to the power m and b to the power n, where this m and n are actually the order of the reaction. Okay, so m is the order of the reaction with respect to A and n is the order of the reaction with respect to B. The overall order of the reaction will be given by the sum of m and n. All right, there is one more topic which is molecularity and order, but that is too trivial. I have not discussed that in this video. All right, so yeah, the rate with respect to each and every constituent of the reaction can be given like this. The coefficient or the stoichiometric coefficient of that particular species goes in the denominator. So you have minus 1 upon A dA by dt. This minus sign tells you that this A is on the reactant side. Then you have minus 1 upon B dB by dt plus 1 by C, because this C is on the product side and D is also on the product side. So that's why you have positive signs for them, whereas you have these coefficient in the denominators. Alright, so this was the basic thing. Now we'll talk about the reaction orders. Okay, so let's talk about this zero order reaction. So for a zero order reaction, let's say a reactant is converting into product. So the differential equation for the zero order reaction will be given by this, that is minus dA by dt will be equals to k naught. If you integrate that, the integrated equation becomes this, that is A is equals to minus kt plus A naught, where A is the final concentration of the reactant, A naught is the initial concentration of the reactant, K is the rate constant, and T is the time for the reaction. Okay, you can also write down the value of the rate constant K naught as A naught minus A upon T. A naught is again the same thing, the initial and final concentration, T is the time. So with this equation you can find out the rate constant value. Then you have a unit of this zero order reaction. The unit is given as moles per liter per second. T half of zero order reaction is given by this expression. This is A naught upon 2 K naught. Now there are certain important graphs also from your zero order reaction. The first one is rate versus time. Now you know from the expression that rate is equals to K naught and A to the power 0, because it's a zero order reaction, so order will be 0. So or you can say that your rate is equals to K naught. So rate is constant with respect to time, so the time will change but the rate will not. So that's why it's a constant curve where this intercept or this value is equals to the rate constant for the zeroth order reaction. The other equation can be derived using this particular expression and by plotting your concentration on the y-axis and time on the x-axis. So if you plot concentration versus time, you will get a negative slope of minus k, and the intercept you will get as a positive intercept of A naught. So these are two important curves or two important graphs from your zero order reaction. Let's talk about the first order reaction. So in the first order reaction, the integrated equation is given as K1 is equals to 1 upon T ln A naught upon A, where A naught is the initial concentration, A is your final concentration, and you know that this is in the natural logarithmic form. Okay, your K1 can also be written as in the log base 10 form. So in terms of log base 10, it will be 2.303 upon T log base 10 A naught upon A. Now, if let's say A1 and A2 are two different concentrations at two different times, T1 and T2, and the overall reaction is a first order reaction, that means the reaction is same, that is A is getting converted into product and it's a first order reaction, but you have two different concentrations of A at two different times. So in that case, the rate constant will be given as 2.303 upon T2 minus T1 log A1 upon A2. So this is very important expression which can help you to find out the rate constant for the first order reaction if you are given with two different concentrations at two different times. The unit of the first order reaction is given as like second inverse or time inverse basically. Half life is independent of the concentration, it's given as 0.693 upon K. Okay, so this is how we calculate half life for the first order reaction. Some important graphs are over here, like rate versus time graph. You know that rate will be equal to K1 and into A. So A is basically concentration which changes with respect to time. So rate and time are basically inversely proportional to each other. So rate of the first order reaction shows exponential decay kind of thing with respect to your time. So that's why this curve is decreasing over here. All right. Now you can also plot this particular graph, that is this K1 is equals to 1 upon T ln A naught upon A. You can plot this equation to get this in this particular form, in which I am plotting ln A on the y axis and time on the x axis. So in that case, the slope will be minus K and the intercept is ln A naught. Okay, so which equation I have used? So I have used this expression, that is K is equals to 1 upon T ln A upon A naught upon A. So basically you can write down K is equals to, or KTK is equals to ln A naught minus ln A. So if you are plotting this ln A on the x-axis, so you can just write down it like ln A will be equal to ln A naught minus K into T. So here you can see that this is what I have plotted on the y-axis, this is what I have plotted on the x-axis. So the slope is minus K and the intercept is ln A naught. So this is how this graph has been plotted. Now one more very simple graph is here regarding this particular equation. If I plot this particular whole thing on the y-axis and if I plot this on the x-axis, if I multiply it on the other side, so I'll have a positive slope of K upon 2.303, and that's what this graph is about. Okay, so these are three important graphs for your first order reaction. Alright, there are some more important expression for your first order reaction. The one is over here. For your gaseous first order reaction, the rate constant is given as K is equals to 2.303 upon T log P naught upon P naught minus Px, where P naught is the initial pressure and P naught minus Px will be the pressure at certain time when some amount of your product will be formed. Okay, for example, if A is giving you some product, let's say, so if let's say initial pressure of this is given as P naught, so initially this will be 0. After some time, let's say its pressure is Px, the pressure of the product is Px, so the pressure corresponding to the reactant will be P naught minus Px, right? So this is going to be substituted over here, and this is basically the pressure at some time t, and this is the pressure at initial position. The next expression is the time required for completion of 1 by nth of a reaction for the first order reaction. Okay, so T is equals to 2.303 upon K log n upon n minus 1 is the expression, where n is which fraction or which factor you want to see that how much time it will take. For example, if I am given with a first order reaction and if I ask that what is the time required for 1 by third of the completion of that reaction, so n value will be 3 over there. Okay, and 1 by third means n will be 3 over there. All right, so like that you have to substitute and you have to just solve and you will get the value of your time required for that. Okay, so it's as simple as that. Just by knowing this expression you can do that. Let's talk about the second order reactions now. So second order reaction is the one in which, let's say, 2A, like 2 moles of A is giving you product, so it's where your both the reactants are of same kind. So the reaction the rate constant is given as K2 is equals to 1 upon T 1 upon A minus 1 upon A naught, where it's 1 upon final concentration minus 1 upon initial concentration of A. Now let's say if you have two different like reacting molecules, you have A and B, two different reacting molecules, and they are giving you product as it is. So in that case, your rate constant K2 will be given as 2.303 upon A minus B into T, and log B A minus X upon A B minus X. What are these terms over here? Let me just tell you quickly. So if let's say A and B are reacting to give you some product, so in that case initial concentration of A and B is taken as small a and small b. After some time after some time t, the product is formed as x moles. So this will be like A minus X, and this will be B minus X. So these are the values. Okay, so this is when time is 0, and this is when some time is equals to t at what you are going to calculate. The next is unit of the second order reaction is given as mole inverse liter per second. T half for the second order reaction is given as 1 upon K2 A naught. If you plot the graph for 1 upon A versus time, you will get a straight line with intercept of 1 upon A naught, and the slope for this is going to be your K2. Okay, so that's what is going to be the slope of this curve. So this is for the second order reaction. Alright, let's talk about the nth order reaction. So for any order reaction, if you are given with, the rate constant will be given by this expression. Remember, this expression is not valid. Okay, this expression is not valid for first order reaction. Okay, for first order reaction the expression is different, so make that thing very clear. So Kn is equals to 1 upon n minus 1, 1 upon A to the power n minus 1 minus 1 upon A naught n to the power n minus 1, where A and A naught are final and initial concentration. N is the order for which you have to calculate. This expression will not be used for first order reaction. For other order reactions, you can use this expression to find out the value of rate constant. Unit of the nth order reaction is given as moles per liter to the power 1 minus n into second inverse, and half lifetime is given as 2 to the power n minus 1 minus 1 K into n minus 1, and initial concentration to the power n minus 1. So these are the very important expression which will help you to find out T half formula or unit for any order reaction. Alright, the next thing is called as your temperature dependence. So generally it is seen that every reaction doubles itself after every 10-degree rise in the temperature. So from there itself, that temperature coefficient comes into play. So temperature coefficient of a reaction is given by rate of a rate constant at T plus 10 degrees Celsius divided by a rate constant at T degree Celsius or T degree Kelvin. Okay, so instead of Celsius you can mention it in Kelvin. So T degree Kelvin and this degree Kelvin. Okay, so you have to find out the rate constant at a particular temperature and the rate constant at 10 degree more temperature of that. Then just take different divide both of them and you will get the temperature coefficient. Alright, the best equation or the equation which basically deals with temperature and rate constant is your Arrhenius equation. Arrhenius equation is given as this, that is K is equals to A e to the power minus EA upon RT, where EA is activation energy, A is pre-exponential factor, R is your gas constant, T is the temperature, K is the rate constant. So if you are doing for two different temperatures of a particular reaction, so if you have a reaction and you are taking it for two different temperatures, so it will have two different rate constant values. So that will be given as log K1 upon K2 is equals to EA upon 2.303 R, in the bracket it's 1 upon T2 minus 1 upon T1. The differential form of your Arrhenius equation is del ln K by del T is equals to EA upon RT square. Okay, these are certain important equations from your Arrhenius equation. Now the graphs which are there, the one of them is where you plot K versus T. So if you plot that, that is directly from your Arrhenius equation, so it will show you exponential rise kind of curve. Okay, so that's what you are going to see. And the other equation is where you can just plot ln K versus 1 upon T. In that case you are going to get a slope of minus EA upon R, and the intercept is ln A. So basically this came from just taking ln to this equation. So if you take ln to this equation, this will become ln K is equals to ln A minus EA upon RT. Now if you plot ln K versus 1 upon T, so this is basically going to give you a slope of this and an intercept of this. Okay, so this is how you have just plotted equations from the Arrhenius form. Now there are certain like special type of reactions. One of them is your parallel reaction. Parallel reaction is one where a certain reactant get converted into two different products B and C with different rate constant K1 and K2. So there are some important equations relating this for the parallel reaction. One of them is like K1 upon K2 is equals to the concentration of B divided by concentration of C. The overall rate constant K is equals to sum of the rate constants for the two different reactions like K1 plus K2. Rate of formation of B, that is dB by dt, is equals to K1A. Rate of formation of C is given by dC by dt, that is equals to K2A, and basically rate of formation of A is going to be given as, or basically it should be rate of decomposition of A, dA by dt, it should be equal to K, like K is your overall rate constant into A, okay, into the concentration of A. So these are some important equations. There are certain more of them, like if you have this parallel reaction, so the concentration of A at certain time t can be calculated by this equation. This is A naught e to the power minus K1 plus K2 into T. The second equation is for the concentration of B at certain time t, so it will be K1 A naught upon K1 plus K2 into 1 minus e to the power minus K1 plus K2 into T. The third one is C is equals to the concentration of C is equals to K2 A naught upon K1 plus K2 and in the bracket it's 1 minus e to the power minus K1 plus K2 into T. Now what's the difference between them? You can see since B is related with rate constant K1, so that's why you have K1 over here, and with C you like that depends upon rate constant K2, so you have K2 over here. Rest whole equation is same for both of them, okay, so you don't have to do much, just remember any one of them. Just make sure K1 and K2 will depend upon the rate constants over here respectively. Now the graph is also important for this type of reaction. So A being on the reactant side, the concentration of A will always decrease. Now here we have considered that K1 is greater than K2. So the rate of formation of B is more than the rate of formation of C. So that's why the curve of B is higher and the curve of C is lower than that. If K2 will be greater than K1, these graphs are going to just interchange their positions. That's all. So C will come above, B will come downwards. The next reaction is your consecutive reactions, in which a particular reactant gets converted into other product, and that product is again getting converted into another product. So this is called consecutive reaction, in which the concentration of A at any time t can be calculated by this expression. This is A naught e to the power minus K1 into T. The concentration of B at any time t can be calculated by this. This is K1 A naught upon K2 minus K1, and in the bracket it's e to the power minus K1t minus e to the power minus K2t. Alright. The next one is the concentration of C at any time t. It's calculated as A naught and it's 1 plus 1 upon K1 minus K2. In the bracket it's K2 e to the power minus K1t minus K1 e to the power minus K2t. So you just have to look upon the expressions, that how they have been written and what are the values that we are going to write down, okay. So you just have to be very careful with these expressions, okay. The formula you should know and how to substitute and solve questions from here. The next one is, if let's say your K2 is very much greater than K1, that means rate of formation of C is very much high as compared to the rate of formation of B. So in that case your concentration of C will be given as A naught, in the bracket it's 1 minus e to the power minus K1t, okay. So that's what is going to be the expression for your concentration of C. So C has two formula, this and this. This is a special kind of formula or special condition where K2 is greater than K1. So if K2 will be greater than K1, obviously you can just neglect this K1 here and you can just neglect this part here. K2 and K2 will get cancelled out and this is what you are going to get. So it has been derived from here itself. Now the graphs over here, just look upon the graph. A being on the reactant side, it will always decrease. B, since it is on the product side for A, so initially it will form and then again it will dissociate, because from B again C is getting formed, right? So that's why B has increased first of all. The concentration, these are all concentration versus time, okay, concentration versus time curve. So initially the concentration of B has increased, but then it suddenly got decreasing. Why it is decreasing? Because B is now converting into C, and C initially it will be smaller, then slowly it will keep on increasing, and it is on the product side, so the concentration of C will always increase, it should not decrease. So these are the different curves for your consecutive reaction. Okay, the next topic is your steady state approximation. In the steady state approximation, generally what happens that there are certain species in a particular reaction, especially those reactions which happen in steps. So there are certain species which are involved in the reaction for very small amount of time. Those are called as reaction intermediates. So here you can see that if A is forming B in an equilibrium reaction kind of thing, where A is forming B and B is again deforming to form A, it's a fast reaction, and then B is getting converted to form product. It's a slow and rate determining step, okay. So this is your rate determining step. So the concentration or the rate of formation of B will be dependent upon the concentration of A, as well as it will be dependent upon the concentration of B in the first step, and the rate will be this much. So the rate of formation of intermediate and the rate of decomposition of intermediate are equal according to the steady state approximation. So if you keep that, so this is the rate of formation of intermediate, this is rate of decomposition of intermediate, so both of them have to be equal. So you can either put equal sign between them, or you can just subtract both of them and compare it with 0. So with that you will get concentration of B to be this much. Now the rate, just put the value of B over here. So you are going to get, okay, I should have written, it should have been A here, okay, so it should have been A. So that's how, so yeah, so you have just substituted the value of B, the concentration of B here, so it became K2 K1 upon K minus 1 into A. Okay, so that's the final rate reaction according to the steady state approximation. So steady state approximation can be applied in many reactions. If the reaction is of multi-step, you just have to put it in such a way that the reaction intermediate will be such that the rate of formation and rate of deformation or rate of decomposition should be equal. Alright. Okay, the next thing is your collision theory. So there are certain points regarding your collision theory. The point says that the reacting molecule must collide with each other before they react. So in order to react two reacting molecule, they have to collide with each other. Now the number of collision per second per unit volume of the reaction is called as your collision frequency, and that's what we denoted by ZAA. Now ZAA is collision frequency when both the atoms are same, okay, when there is a homoatomic kind of system. So in that case we'll write down ZAA, and this will be 2n square d square 8 pi kt upon mu under root of that. Okay, so you know that n is the number of molecules which are colliding, d is the diameter of that, or you can say the distance between the two atoms, and then you have 8 pi and k is your Boltzmann constant, T is the temperature, mu is your reduced mass. Then if the reacting molecules are different, if you have two different atoms which are colliding to give you product, in that case Z will be converted into ZAB, and ZAB is equals to NaNb DAB square and 8 pi kt upon mu under root. So now here Na and Nb are number of molecules of A and number of molecules of B respectively. DAV is average diameter, which is calculated as dA plus dB by 2. So that's diameter of A plus diameter of B divided by 2. And 8 pi kt, again all the other factors or all the other terms or all the other variables are same. Okay, like K is Boltzmann constant, is the temperature, mu is your reduced mass. Okay, so to get the rate of the reaction, collision number is also multiplied. So the rate of the reaction, this collision number multiplied or collision frequency multiplied by the energy factor. So overall rate of the reaction according to the collision theory is this much: NaNb DAV square 8 pi kt upon mu under root and e to the power minus Ea upon kt, where Ea is your activation energy, K is Boltzmann constant, T is the temperature. There is one more factor which was added later on, which is called as steric factor, denoted by P. Now P is the steric factor which says that colliding molecule should have proper orientation for completion of the reaction. So a fraction of collision having proper orientation for conversion of reactant to product is called steric factor. So basically a particular reacting species should have a particular orientation in order to collide and form the product. If they are not in a proper orientation, they won't form the product. So this steric factor is denoted by P, and the overall rate is given as P ZAB. So this is like a steric factor multiplied by the collision factor multiplied by the energy factor. So all the three factors are multiplied to get the overall reaction rate. This is from your collision theory. The next theory which just advanced this a little bit, that was your transition state theory. The transition state theory suggested that the colliding molecule they do not just collide and form the product, they undergo collision, they form a transition state or activated complex and then form product. Just like you can see over here, this AB hash is your activated complex, okay, or transition state. So this A and B are going to collide to form this activated complex, and then they are going to form the product. Now EA is some additional amount of energy that must be absorbed by the reactant in their ground state to allow them to reach transition state. If they reach transition state, then only the reaction proceeds. So if you see this exothermic reaction curve or this reaction profile diagram, you will see you have this reacting molecule and here you have product. So the energy required for the reactant to get converted into product is this much. This is EA. So EA is the activation energy for the forward reaction. Now you can also have this energy difference. This is your transition state here, okay. So the energy difference between the product and the transition state is called as EA dash. EA dash will be the activation energy for the backward reaction, or for the reaction where product will get converted into reactant back. The difference between the potential energies of reactant and product is called as your delta H. Exothermic reactions have a negative delta H, right? Okay, the next one is endothermic reaction. All the things will be same except your delta H. Here delta H will be positive, okay, and in this case delta H is negative. All right, rest of the things will be same, like transition state will be there, activation energy and other things will be same here. Okay, the rate constant for your activation step, that is given as concentration of your activated complex divided by the concentration of reacting molecules, like concentration of A and concentration of B. So C hash is the concentration of activated complex, Ca is concentration of A, Cb is concentration of B. Now if you use statistical thermodynamics, you can find out the rate constant for the activated complex. So that will be given as Q hash divided by Qa Qb e to the power minus Ea by Rt. Now Q hash is your partition function of the activated molecule, Q and Qb are partition functions of A and B. Okay, so this comes from your statistical thermodynamics. It has been included over here to find that out according to the transition state theory. Now here you can see that this is the final equation for calculating the rate constant of the overall reaction. So it's equals to Kt, where K is your Boltzmann constant, is the temperature, H is your Planck's constant, Q hash upon Qa Qb e to the power minus Ea upon Rt. So that's the overall rate constant for the reaction. The next thing is transmission coefficient. So transmission coefficient tells, it was seen that it's not necessary that all the activated complex is going to form the product. Okay, so it's not necessary that all activated complex are going to get converted into product. So some of them, or the fraction of the activated complex which get converted into product, is given by your transmission coefficient. So transmission coefficient is denoted by capital K, and it tells you, or it suggests, or it tells you the fraction of the molecule which get converted from activated complex to the product. So K is equals to this capital K, kBt upon H, Q hash upon Qa Qb e to the power minus E upon Rt. You can see the rest of the equation is same, only this capital K has been included. Now for most of the reactions, this capital K, or this transmission coefficient, is unity. It has a value of 1. That means that in most of the reactions all the activated complex get converted into product. So this you should know. Alright, let's take the next thing, that is Eyring's equation. It's most important equation and it has been asked many times in your GATE and CSIR net exam. So transition state theory, when it is expressed in the form of thermodynamic functions and instead of partition functions. So earlier you have seen that the equation were expressed in terms of partition functions. Now we are going to express the expression in terms of thermodynamic functions. So that's what Eyring has done, and that's what is Eyring's equation is about. So Ks is equals to kBt, okay, divided by H, e to the power minus delta H hash by Rt into e to the power minus delta S hash by Rt. Now here your delta H hash and delta S hash are basically enthalpy and entropy of activated complexes respectively. T is the temperature, R is your universal gas constant. Okay, fine. The next is your Lindemann theory of unimolecular reaction. It has been seen that a unimolecular reaction can also be giving you a certain product. In that that was given by Lindemann. So according to that theory, if A collides with the same molecule, it will just activate that molecule, and that activated complex or that activated molecule is going to form the product. Now the rate of the formation of product depends upon K2 into concentration of this activated A. So that is going to be equal to K1 K2 A square upon K minus 1 A plus K2. I have directly written the equation, whole derivation is there. Okay, so at high pressure what happens, that at high pressure basically your K minus 1 into A is quite more than your K2. Okay, so at high pressure what happens, that K minus 1 into A is quite more than your K2, and that's why your K2 you can just neglect that. So you just have K minus 1 into A and A will get cancelled out. You will get K1 K2 A upon K minus 1. So the reaction is of first order over here. Okay, so at high pressure the reaction is of first order. At low pressure what happens, that your K2 is quite more than your K minus 1A. So in that case you can just neglect this K minus 1A. You will have K2 in the denominator, that will just cancel out this K2. You will only left out with K1A square. So this is basically a second order reaction. So if you plot this equation of rate versus A, So you are going to get this equation like this. So initially the reaction is of first order, and after some time or at higher pressure the reaction becomes of second order. So you should know all these things. The next part of your chemical kinetics is your enzyme catalysis. In the enzyme catalysis, it is said that your enzyme reacts with a substrate to form enzyme substrate complex. This enzyme substrate complex will form product and it will give the enzyme back. So enzyme participate in the reaction and they come out of the reaction. It's kind of it works as a kind of your biocatalysts. Okay, so the rate of the reaction is given as K2 E naught into S divided by Km plus S, where I'll just write down the terms over here. So your E naught is total concentration of enzyme in the reaction, your S is concentration of substrate, okay, here Km is Michaelis Menten constant. All right, now you should also know that this E is basically E naught is basically equal to your E plus ES. Now here this E naught is the total concentration of your enzyme. E is the enzyme which is freely available. Okay, these are free enzymes. Concentration of your, these are your free enzyme, and ES is your enzyme substrate complex. So the concentration of free enzyme plus the concentration of enzyme which has formed substrate, which has formed complex. If you add both of them, you will get the total enzyme. That's what this expression is telling you. So here Km is your Michaelis Menten constant and it's given as K minus 1 plus K2 upon K1. Now you should know this expression. Okay, this expression is going to help you a lot to solve a lot of many things. So rate will be equal to K2 E naught into S upon Km plus S. Now if you have very less substrate concentration, in that particular case you can just neglect that from the denominator. You will just have Km in the denominator and the reaction becomes of first order over here. Okay, so the reaction is of first order when substrate concentration is very less. Now if you have higher substrate concentration, the substrate is very high in the reaction, in that particular case you can just neglect this Km over here and you can just cancel out this substrate concentration. So the reaction becomes of zero order with respect to the substrate concentration. Remember these everything we are just talking about the order with respect to substrate concentration. Okay, so order with respect to substrate concentration. All right, the next important thing is the graph from here. Okay, so when your total enzyme concentration is equals to the concentration of enzyme substrate complex, that means that when all the enzyme which you have given to the reaction, all of them have formed the enzyme substrate complex. If that happens, in that case the rate becomes maximum, and that's what we call it as Vmax or Vm. So Vm or Vmax tells you the maximum rate when all the enzyme which was present in the reaction has now formed a complex with the substrate. So this is equals to K2 E naught. Now K2 is called as your turnover number in this reaction. Okay, so K2 is called as turnover number. Remember that if in the question or if in the exam they are asking you to calculate turnover number, so basically they are asking you to find out your K2 value. Now if the number so what is turnover number? It is the number of molecules converted in unit time by one molecule of enzyme. Okay, so how many molecules in a unit time is getting converted by the enzyme, that's called as your turnover number. Now you know rate is equals to Vmax into substrate concentration upon Km plus S. Let's talk about the other very important equation that is called as your Lineweaver-Burke plot. This is one of the most important expression in your enzyme catalysis. The same relation which we have seen, rate is equals to Vmax into substrate concentration divided by Km plus substrate concentration. If you just take reciprocal of this equation and divide them separately, you are going to get 1 upon rate is equals to Km upon Vm into substrate concentration plus 1 upon Vm. Now if you are going to plot 1 upon rate versus 1 upon substrate concentration, so this particular part which is along with this, so this is on the y-axis, this is on the x-axis, so this is what you are going to get as slope and this is what you are going to get as intercept. So just put it over here. You have just plotted rate 1 by rate versus 1 by substrate concentration, slope is Km upon Vm and your intercept is 1 upon Vm. Now you know what are the terms, right? Km is your Michaelis Menten constant, Vm is your maximum rate of the reaction, okay, or max rate of the reaction. The next and the final equation which we have from the enzyme catalysis, that is Eadie Hosfstee plot. Okay, so in that the same expression which we have for the Lineweaver-Burke plot, we have just like rearranged it in this term, that we got rate is equals to minus Km into rate upon substrate concentration plus Vm. Okay, or this expression can also be written like this, that is V is equals to minus Km into V upon substrate concentration and plus Vm, where V is basically denoting the rate. Okay, and now the graph is basically plotted between like V versus V upon substrate concentration. So in that case you get a negative slope. The slope is equals to minus Km, and your intercept is equals to your Vm. So in that particular way, we have done all the three parts of your chemical kinetics. We have done the basic reaction part, we have done the transition state theory part, and we have also done the enzyme catalysis part. So that's all for this video, guys. Thank you so much for watching this video. I hope you guys like this video. If you like the video, give it a like, and if you have any WhatsApp group or any Telegram group, just share this video in that particular group. And if you have not subscribed to the channel yet, please do subscribe to the channel, and I'll see you guys in the next video. Till then, have a great day and bye bye.